Hello everyone. In this video we are going to talk about the central force motion and orbital mechanics. So if you consider here a satellite orbiting the Earth, if you neglect the effect of the air, because let's say the density of the air at the altitude the satellite is orbiting is negligible, very small, then the only force acting on the satellite is the weight of it, which of course has to be modified for its distance from the center of the Earth, right? Because mg is when you are at the radius of the Earth, right? When you have a distance from the center of the Earth, which is considerably bigger than the radius of the Earth. So here, this is the radius of the Earth. When your r, the radial distance, which is from here to here, this whole thing is r. When this is bigger than the radius of the Earth, significantly bigger, then your gravity is, as you know, it's inversely proportional to the radial distance squared. So it is going to be smaller than the mg, right? And so your, as you know, the Newton law of gravity says if you have two masses, right, m1 and m2, in this case m and me, and the radius is r, then the gravitational force between them, F of g, is equal to the universal gravity constant g times m1 times m2 divided by r squared, correct? So this is the gravity force that you have when radius is arbitrary r. Now at this surface of the Earth, this gravity force is mg in magnitude. It's equal to g times me times m divided by radius of the Earth squared. And if you compare these two or divide them, correct? If you just divide, you'll see the gravity force divided by mg is equal to what? If you simplify, the m will go away, me, g, they will all go away, and so you will get re squared divided by r squared. And now if you just multiply by mg, you'll see that the gravity force is going to be mg re squared divided by r squared. And that is what you have over here, okay? This is the gravity force at altitude r, which is considerably bigger than the radius of the Earth, okay? So that's why we have this formula instead of simple mg. But clearly you see it is directed toward the center of the big mass. That's why we call it central motion for that satellite. And now that we have that, let's write down the equation of motion, see what we get. So summation of the forces along the r direction is equal to that force, and it's negative because it's opposite to the direction of unit vector er. So you will get negative mg re squared divided by small r squared. This is equal to mass times acceleration radial, and if you know acceleration radial was r double dot minus r theta dot squared. In the theta direction, there is no force. If there was effect of air, then you will definitely get a component for that in the r direction and a component of that in the theta direction. But here it's 0, and this is equal to ma theta, and a theta, if you remember, was r theta double dot plus 2r dot theta dot. Okay, and I'm going to number my equations 1 and 2, and now let's see what we can get from these equations. So first thing first, I can get rid of m, so I get rid of m here, and I simplify m with 0. Now if you look at equation 2 looks a little bit simpler because it doesn't have the constant term. And I might first take a look at equation 2 before going back to 1. The problem here with What we really need here is a solution like r as a function of t or r as a function of theta. That's what we need. Okay, preferably r as a function of theta, maybe. Why? Not preferably. Why? Because here, if you do r versus theta, then you can draw a simple polar plot of the orbit. Now, the problem is this. If you want to do any of these, the problem is the ODs are coupled. Okay, in both ODs we have r terms and theta terms. And so you cannot easily get an analytic solution unless you somehow decouple them, which means get one equation only in terms of r, one equation maybe only in terms of theta. If you can do that, then solving it analytically is way easier. So here I'm solving two ODEs at the same time, which are coupled. And the best thing, if you can, is to decouple these. And as I said, equation 2 looks easier because it has a zero term. And so what can we do? How can we manipulate 2 to get a simpler form than this one? Well, what you can do here is, if you take the time derivative of this term, r squared theta dot. If you take time derivative of this term, which is none of these terms, of course, if you do that, what would you get? This is a product, so it's going to be time derivative of r squared, which, if you know based on the chain rule, it is going to be 2r dot multiplied by the second term, and then plus first term times the derivative of the second term, which is theta double dot. Now, if you look at this one against this one, they are very similar, except that this one is missing an r, or if you multiply this by an r term, you will exactly get the bottom one, right? So all I need to do is I multiply this by 1 over r, and then it will give me what? The r's would cancel, so you will get 2r dot theta dot, and then plus r times theta double dot, correct? One r term would go away. And now this one is exactly the same as this one, right? And guess what? This one is equal to 0. So now I can say this 1 over r time derivative is equal to what? 0. Good. So I converted my addition to a product. And it's always easier when it's in product, because when the product of two things is 0, it means either the first one is 0 or the second one is 0 or both. Now, the good thing is this first term here cannot be 0 because it needs an infinite radius, which is really not we are looking into. So when that is not 0, it means the second term, this time derivative, has to be 0. And when time derivative of anything is 0, it means that entity has to be constant. Good? Okay, now what constant? How much is this constant? Well, since it's constant, it has to be the same as its initial value, right? At time 0, at time 1, 2, whatever, this value is not going to change. But how much was this guy in the beginning? Well, another way I can write this, I can write it as r times r theta dot, correct? And what is r theta dot? Well, if you remember from the lecture I had on cylindrical coordinate or polar coordinate, this guy is what we call v theta, the theta component of the velocity, right? If you remember, in cylindrical coordinate or polar coordinate, the velocity of the particle is in polar, it is r dot er plus r theta dot e theta, correct? So this guy we called VR, this guy we called v theta. So here I'm looking into what? Into v theta. So fine. So it means the product of r and v theta at any point is not going to change. Good. So I can say this should be equal to its initial value, which is r at time 0 times what? V theta at time 0. If I had these two initial values, then their product should be the same as r squared theta at any time. Now, how much are these? Well, when you're launching the satellite into orbit and then giving it an initial velocity so that the exact shape of the orbit is determined, the initial condition is like this. So this is your Earth, this is the satellite. You have moved it from the sun, the surface of the Earth, all the way to the radius of r0. So this r0 is your launch radius into the orbit, correct? And what you do, you give it some transverse velocity v theta at time 0, which is equal to v0. And there is not any VR at time 0. So when you put it in the orbit, you're not giving it any further radial speed, because if you do, then it means your r0 is not going to be constant, and after a fraction of a second you are going to get bigger and bigger radius. So all you do, your launch velocity that you use to determine the shape of the orbit is going to be only in the theta direction, not in the r direction. So I can say that my initial v theta is the same as what? The total launch velocity into the orbit, and my initial r is of course my launch altitude, correct? So this is my launch velocity, this is my launch altitude into the orbit, and so I can say this is equal to, as I said, r0 times what? v0. Good. So now r squared theta dot is equal to the constant, what constant? r0 v0, which we will determine, we will assign to the satellite. So now let's write it down. R squared theta dot is equal to r0 times v0. So I wrote my equation number 2 into an easier version. And now what's the good about it? Well, the good thing is this. If you look at equation number 1, the only term here that is not based on r is this guy here, theta dots, or theta dot squared. If I could somehow replace this theta dot term with an r term, then equation 1 will be fully in terms of r, which means my ODEs are decoupled. So if I can somehow replace the theta dot into 1, then I get 1 fully r ODE, and I can get that. Why? Because now I can use this new equation. And in this new equation, I can calculate theta dot. So this is going to be r0 v0 divided by what? R squared. You see, now theta dot is written in terms of r. So now if I go ahead and plug 3 into 1, then I will get negative g r e squared over r squared, which is the left hand side, equals r double dot minus r times this guy squared, theta dot squared. And here, this is r, this is going to be r to the 4. Okay, so you can simplify, you will get r cubed. So now if you do it, you will get r double dot minus r squared, r not squared being not squared, divided by r cubed is equal to negative g r e squared over r squared. And now this is that ODE I was talking about, pure in terms of r. There is no theta in it, so I could decouple my r. The problem is this is a second order ODE which is nonlinear, because I have r squared term and r cubic term, and they are in the denominator. So is there any way that I can convert this nonlinear ODE now into something linear, which I can easily solve? And the answer is yes, there is. So here I change my variable from R to a new one U. So I go ahead and define my new variable U, which is 1 over R. Let me see if I can make this a little bit darker. Why do I do that? Because here I have a bunch of terms of R in the denominator. So from here, clearly R is 1 over U, or for 1 over these R's, I can replace them with U squared, U cubed, and so on. Okay, so these two terms is going to be like U squared and U cubed. The thing is, what about this R double dot term? Okay, how can I convert that into a U term, or U dot, or U double dot term? So the first thing I do, I take a reciprocal. R becomes 1 over U. And now I take a time derivative from this. It is going to be R dot is equal to negative U dot over U squared, right? And now the question is there any way that I can deal with this U dot term? So I write it as negative 1 over U squared U dot, but U dot, which is du over dt, correct? I will use the chain rule here, and I write it as negative 1 over U squared, and then for du over dt, I write it as du over d theta, right? And then d theta over dt, which is theta dot. Okay, so here I'm trying to use the chain rule. Now, if you remember, your theta dot was what? Was R naught V naught over R squared. You can also, in terms of this new variable, you can write your theta dot, since 1 over R is U, you can write it as R naught V naught U squared, right? Because U is 1 over R. So this guy here, I'm going to plug it down into this equation for theta dot, right? So it is going to be R dot is equal to negative 1 over U squared du over d theta R naught V naught times U squared. And what's the good thing about it? Well, if I plug it in and paying attention here, I have a U squared term in the denominator, and when this guy comes, I have a U squared term in the numerator. So that U squared and this U squared would cancel. So you will get what? You will get negative R naught V naught times what? Du over d theta. This guy is going to be equal to R dot. You see, so my R dot term is now getting a simpler form. And now I take another derivative, because what I need to replace in here is actually the R double dot term in equation number 4. So let me write it down here, that R dot was equal to negative R naught V naught, which are constants, du over d theta. Good. Now from this, I'll take another time derivative. And that gives me that R double dot is equal to, let's keep this negative R naught V naught out of the way because it's constant. So it's du over d theta, but time derivative of it, right? And this is a theta derivative, that's a time derivative. So what I can do is to do the chain rule. Instead of taking time derivative of this u over d theta, I take a what? I take a theta derivative out of it. So it is going to be d over d theta of du over d theta. But look, the denominators are not the same, so I need to multiply that by d theta over d t. When I do that, it's kind of like these two are canceling, and I get my dt in the denominator back. And guess what? Again, I have d theta over dt, or theta dot, which I need to replace it again from this top equation. You see? So if I do that, what happens? I will get r double dot to be equal to negative r naught v naught. This guy is the second time derivative of u with respect to theta. And that one is clearly what? R naught v naught u squared. Right? So if you simplify it, it is going to be negative r squared, r naught squared, v naught squared, u squared, second derivative of u with respect to theta. And now this one, if I call this guy equation number 6, and I call this top one, which I needed 5 maybe. If I plug in 6 and this definition here, let me call this one 5 actually, because that one I did not give a number to, so I can get rid of that. So if I plug in 5 and 6 into 4, what happens? So this is what I'm going to do. 5 and 6 into 4, right? I'm going to get negative r naught squared, v naught squared, u squared, second derivative of u with respect to theta. That's the first term. Minus r naught squared, v naught squared. For r 1 over r cubed, I use u cubed. So it's going to be minus r naught squared, v naught squared, and then u cubed is equal to and then for this term it's going to be negative g r e squared times u squared. And now what's the good thing? The good thing is I can get rid of u squared in each side. Why can I divide? Because u can never be 0. Because u is 1 over r, and r only needs to be infinite for u to be 0, which is not going to happen. So u squared, or u, is never 0, therefore I can easily divide both sides by it. And now I get a nice ODE. I get a beautiful one, right? I get a beautiful one, and I can even divide by r squared v naught squared as well. So if I do that, this one gonna go away, this one gonna go away, and then it is going to appear on this side. Even I can get rid of a negative if I want. So negative goes, and negative goes, and negative goes. And then I will get second derivative of u with respect to theta squared, with respect to theta, and then plus u is equal to re squared over r naught squared v naught squared. And guess what? Times g, of course. This is a very beautiful second order linear ODE with constant right hand side, with constant coefficients, and everybody who passed a differential equation course can easily solve this. You know that u of theta is going to be a homogeneous u solution plus a particular u solution. The homogeneous is when you set the right hand side equal to 0. So what you have is second derivative of u with respect to theta plus u equals 0, you form the characteristic equation. The characteristic equation is going to be s squared plus 1 equals 0, which has complex roots plus minus I. And you know, when the roots are complex, it means the homogeneous solution is what? Is a harmonic function. So it is going to be like a times sine of theta plus b times cosine of theta. So that is your homogeneous solution. And your particular solution depends on the form of the right-hand side. Now the right-hand side is just a constant number, which counts as a polynomial of order 0. So the particular solution has to be also a polynomial with the same order, okay, unless one of the roots of the characteristic is equal to 0, which we don't have here. So since this is constant, your particular solution is going to be the same constant. If you choose u to be just this constant, the second time derivative of it with respect to any second theta derivative of it is 0. So that very constant term could be your particular solution, which you can just write it down. That's it. You found u as a function of what? Theta. That's brilliant, right? The only thing is, what is constant A, what is constant B? Once I determine A and B from my initial conditions, I know perfectly u as a function of theta, and then that is equal to 1 over r. So then I can find r as a function of theta, which is exactly what I want. So before anything happens, we need to find the constants A and B through initial conditions. Well, how can I find them? If you remember, when we go back, I said when you launch the satellite, what you have is your, here. There is no radial velocity, there is only tangential velocity, and r at time 0 is what? R naught. And r dot is 0, r theta dot is v naught. So these are my initial conditions, and let's go and try to use them. Okay? So here, depending on what we choose for my initial theta, and here I choose my initial theta to be 0. Okay? It's arbitrary. I can choose my reference to be at 0 angle there. So for example, you might say, well, here it doesn't look like, for example, if you launch it like this, your initial theta to be 0. Well, it doesn't matter. I can rotate my r theta and set my x-axis to pass through that initial theta, and then now my initial theta is 0. So it's not a big deal. It's not going to change anything, this assumption of initial angle to be 0. So if I choose that, then I can say that at initial theta, correct? What's r? R equals r naught. Therefore, u at time 0 is equal to 1 over r naught. So if I plug in theta of 0 here, my u should be 1 over r. Okay, that's one of my initial conditions. Let's use that. So here I'm going to plug in theta of 0, which makes this whole thing 0, makes this guy 1. That guy stays as a constant. And you will get 1 over r naught is equal to b plus GRE squared over r naught squared v naught squared. Therefore, your b constant becomes 1 over r naught minus GRE squared over r naught squared v naught squared. There we go. I found one of them. Now let's number my equations again. That's 7. This is 8. Now let's apply the other initial condition I have. And what is that? Well, at time 0, if you remember, the VR, which is dr over dt, so VR at t of 0, which is r dot at t of 0, this guy was 0. But what was r dot in terms of u? Because here everything is in terms of u, not r. So I need to go back and find my r dot, and if you look here, my r dot was negative r naught v naught du over d theta. So let's write it down, negative r naught v naught du over d theta at time 0. This whole thing has to be 0. At time 0, this is 0. And guess what? It is r naught and v naught, which cannot be 0. Therefore, it means your first time derivative of u with respect to theta at time 0 has to be 0. So this is your second initial condition. The first one was this, that at theta of 0, u was 1 over r naught. This was one of your initial conditions, so I can call it initial condition 1. And this is your second initial condition. This is your initial condition 2. Okay. So now for that, I need to look at the derivative of u with respect to theta, and at time 0, it should be equal to 0. Well, derivative of u with respect to theta, this constant term going to go away. Derivative of a sine is going to be a cosine. Derivative of b cosine is negative b sine. And if you plug in 0 in it, because theta of 0 is 0, this negative sine term would go away. You will only down to a cosine of 0, which is 1. So the whole derivative of this with respect to theta at time 0 is going to be a. So all it is, it means this thing is equal to a, and it means a has to be what? 0. So this is your second thing. The constant a ought to be 0, and that's equation 9. So now if you plug in 9 and 8 into 7, you'll get your final solution. So 8 and 9 into 7, it means u, which is 1 over r, is equal to a is completely what? 0, so the first term going away. That constant b times cosine theta, and b is that guy over there. And then you have the constant term on that side as well. So GRE squared over r naught squared v naught squared, and correct, and that is going to be GRE squared over again r naught squared v naught squared. Okay, and you can see these two terms here are the same thing, correct? This term and this term. Good. So here, again, I'm going to define a new term. So I will say define a new term. We call it epsilon or eccentricity. And we define this to be R naught times V naught squared over G times RE squared minus 1. So it's similar to the reciprocal of this, except for the 1 extra R naught and then minus 1. And that makes writing this a little bit nicer. But before that, what I can do is I factor out 1 over R naught out of this, so I write it as 1 over R naught times 1 minus G R E squared divided by R naught V naught squared. And this clearly, again, I can factor out 1 over R naught. And this is going to be GRE squared over R naught V naught squared. Okay, so I write them like that. Well, from here, based on this new definition that I did, this guy here that I'm interested in, R naught V naught squared over GRE squared, it is going to be 1 plus epsilon. And since in this top equation I have what? I have the reciprocal of that. So what I have in these top equations, this term, is going to be 1 over 1 plus epsilon. Okay, so now this guy here is going to go in the top equation. It goes here and it goes here. And if you do that, then you will get 1 over R is equal to 1 over R naught, which you had over here, times 1 minus 1 over 1 plus epsilon times cosine of theta. And then here it's going to be 1 over R naught times 1 over 1 plus epsilon. Okay? And if you rearrange this and write it in terms of R naught and epsilon, you will get R over R naught to be equal to 1 plus epsilon divided by 1 plus epsilon times cosine of theta. And this is the nicest equation that you can get out of this problem, which is actually nice. Why? Because it is related to conic sections that you probably learned in geometry. And this epsilon can tell you a lot about the shape of the orbit. So clearly here you have R as a function of theta, because epsilon is a constant number and R naught is a constant number. Remember, that's your epsilon, is pure constant. And R naught is constant. So clearly that's your R as a function of what? This is R of theta. Now, why this is an easy formula to understand? Well, let's look at different scenarios. For example, if your epsilon number is equal to 0, what does that mean? If you plug in 0 in this top equation, it means R over R naught is going to be equal to 1. And it means R equal R naught. So at whatever height that you have, or altitude that you have launched the satellite in the beginning, so if this is your initial R naught, it's not going to change. So what does that mean? The R, the actual radius, is always going to be equal to what? r naught. So it means the path is a circle, or it's a circle, or circular orbit. Right? So if eccentricity is 0, it means your satellite is going to go around the circle. And 0 means what? Means this number is 0, which means r naught v naught squared should be equal to what? GR e squared. G and RE are fixed numbers. And if you choose a specific radius, if you fix your v naught such that this entity is equal to 0, then you will have a circular path around the Earth. Okay, so if you want a circular path, what does that mean? It means that your r naught v naught squared over GRE squared should be equal to 1. If this is 1, then subtraction of that from 1 is 0, and it means your speed that you need, the magnitude of velocity that you need for the launch, is going to be RE times square root of G over R naught. So if you choose your launch velocity based on your launch altitude to follow this formula, excuse me, then you will have a circular path. So if you want your satellite to follow a circular path just around the Earth with the fixed radius of r naught, that's how much of the initial launch velocity that you need. Okay, so epsilon of 1 means circular path. Now what if epsilon is not 0? For example, what if epsilon is between 0 to 1? So what if epsilon is bigger than 0 but less than 1? What does that mean? Well, let's go back, look at your equation. So this one was what? Was 1 plus epsilon divided by 1 plus epsilon cosine theta. So what does that mean? Well, your theta, when it changes, it is going to what? -1, 0, +1, and it oscillates. So your numerator and denominator are going to sometimes be numerator bigger than denominator, sometimes numerator equal to denominator, sometimes smaller than denominator, right? Is that right? Correct. So for example, when theta is 0 or 2 pi, r and r naught are the same. When theta is pi, this is going to be 1 plus epsilon over 1 minus epsilon. Right? And that's where your numerator is, because numerator is constant. Your numerator is the largest, your denominator is the smallest. And that means this ratio is the largest, which means your r is the largest. Correct? And when theta changes between 0 to -1 and 1, your denominator, in general, as long as theta is less than 1, which it is always in magnitude, unless theta is 0 and 2 pi, your denominator is always less than numerator, which means the ratio is bigger than 1, so means r is bigger than r naught. So here, that means r is bigger than r naught or equal to r naught only if theta is 0 and 2 pi. And you can easily show that in this case, if this is the Earth and this is the initial satellite launch at, let's say I launch it at theta of 0. Let's say I launch it here, just for simplicity. So this is my r naught, this distance. And this is theta of 0. At theta of 0 and 2 pi, you will get r equal r naught. At theta of pi, you will get 1 plus epsilon over 1 minus epsilon, which is the largest, and between them r is always bigger than r naught, but not as big as 1 plus epsilon over 1 minus epsilon. And if you plot this, what you will get is an ellipse like that. Okay, where this is your r max, this is your r min, which is the same as r naught. And your r max is 1 plus epsilon over 1 minus epsilon times r naught, of course. Okay, the equation will be an elliptic equation. And you can show that if you want. It's not that hard to show it is elliptic. So all you need is to cross multiply both sides. You will get r plus r epsilon cosine theta is equal to r naught times 1 plus epsilon. Correct? And now can I show that this guy is the equation of an ellipse? I assume so. If you, for r, you plug in square root of x squared plus y squared. If you call this whole thing constant c, and you know r cosine theta is x, so this is going to be plus epsilon times x is equal to constant c. And now what you need is to take epsilon x to the other side and square them. Then you will get x squared plus y squared is equal to c minus epsilon x, the whole thing squared, which is going to be c squared plus epsilon squared x squared minus 2 epsilon cx. And now what you can do is to bring these two terms to the left hand side, and if you do that, you will get x squared times 1 minus epsilon squared plus 2c epsilon x plus y squared is equal to c squared, which clearly is the equation of an ellipse, right? You know, this is the equation of an ellipse, where the center is definitely not at 0 and 0. And you see why it's an ellipse, because the coefficients of x squared and y squared term are different coefficients, correct? So this is an ellipse, and the center is not at 0, 0. If you want, you can basically square these terms up, and you'll definitely see that the equation is not the equation of an ellipse. So all you need is to take the square root of this, right? So it is going to be something like this. This minus something squared, that is going to be, or plus something squared, that is going to be this term here over that. Correct? If you square that, you will get this plus 2 times the product of them. Yes. And you need this extra term here. So you have to add it to both sides. Which if you do, you will get c squared over 1 minus epsilon squared. Okay, and definitely, as you can see, this is the equation of an ellipse where the center is at negative of this point and y of 0. The coefficients of x and y are different, and definitely this is the equation of an ellipse. Okay, so if epsilon is between 0 to 1, you will get an elliptical. Orbit. And then you can show that for other cases where epsilon is 1, then you will get a parabola. Epsilon bigger than 1, you will get a hyperbola, okay, which is not super hard to show. Now here, if epsilon is 1, you definitely see that the center is going to go to infinity, and it is, and that's what makes this guy go to a parabola. So if epsilon is 1, then you will have a parabolic orbit, and if epsilon is bigger than 1, then you will get a hyperbolic orbit. Okay, so bigger than 1 hyperbolic, equal to 1 parabolic, between 0 to 1 elliptic, and equal to 0 it is circular orbit. So this is the equation of r as a function of theta, and you saw that based on the value of epsilon you can have 4 different types of behaviors. So if I want to show it all in one figure for you, so that I want to summarize everything. So then you have something like this. As long as I can move it a little bit. See if I can move any of these guys. Oh. Okay. So let's say this is the Earth. Then we have the circular orbit. Then we have the elliptic orbit. Then we have the parabola, and then we have the hyperbola. So this is my launch position, and this is the Earth. It's not a good writing. Very fast. Let me change it. Oh, quite a small font, isn't it? Let me make it larger. There we go. And that small thing is my satellite. And then, as I said, I can have this scenario, and then I can also have this scenario. So this is epsilon bigger than 1. This is epsilon equal to 1 parabola. This red one is epsilon between 0 to 1 elliptic. And this blue one is epsilon equal to 0 circular. Okay, where again r over r naught is equal to 1 plus epsilon over 1 plus epsilon cosine of theta, and epsilon is defined as r naught v naught squared over GR A squared. minus 1. So this is the summary of this orbital mechanics. And we learned that for what velocity we can make the satellite go around a circle. Correct? That was, if you remember, v of the circular orbit was equal to RE times square root of G over R naught. Okay, if you make it like that, then you have circular, and then here at epsilon of 1, what happens? At epsilon of 1 is when your satellite is going to get away from the Earth and it doesn't come back. It doesn't really orbit. So at epsilon of 1 and epsilon of bigger than 1, the correct term is, I don't call them orbit, I call them a path. Okay, it's not really correct to call them an orbit because they don't come back. They keep drifting from the Earth. And this is what we want, something like the Voyagers or stuff like that, that they travel interplanetary, right? We want to send something from the Earth to go to, let's say, the Moon, the Mars, or other planets. If we want some satellite to transfer information from the Earth, then this is if we want them to go on a circle around the Earth and keep a constant distance. If we make it a little bit bigger than this, they're going to go elliptic, which at some point they're going to get far away from the Earth. At some point they're going to get closer to the Earth, which could not be as useful as if they keep a constant distance from the Earth. So this is an important velocity here. And the other one is, again, at this limit when epsilon is 1 and when you send it to other planets. So if epsilon is 1, which is this guy, if epsilon is 1, so this was for epsilon of 0. If epsilon is 1, what happens? So this whole thing becomes 1, and then you take 1 to the other side, becomes 2. And so your v of, we call it escape velocity, is going to be RE times square root of 2g over R naught. So this is what we call the escape velocity. And as long as the launch velocity v naught is bigger than this, okay, as long as the launch velocity is equal or bigger than this number, your satellite, your whatever you send to the space is not going to come back to the Earth. It's not going to orbit. It is going to drift from the Earth. Okay, so we call it the escape velocity. And that's the formula for it. It does depend on the value of R naught, and depending on what altitude you launch, then you will get a value for the escape velocity. Okay, so it depends on where you are launching. It definitely depends on R naught. If you make RE to be this R naught to be the same as RE, so you're launching something from the surface of the Earth, okay, then how much is this number going to be? So let's just give a rough estimate of this. If R naught equal RE, if you launch something from the surface of the Earth, then this escape velocity is going to be what? It is going to be square root of 2GRE. And you know the average of the radius for the Earth is 6370 kilometers. Okay, that's the average radius of the Earth, because the radius of the Earth is not constant. Based on altitude and latitude and longitude, it does change a little bit. But if we assume the average and we plug in into this formula, let's just do that. So square root of 2 times g times 6370000 is in meters. And then you will get basically 1.1179 times 10 to the 4, or basically 11,179. So 11,179 meters per second, or 11 kilometers per second. Or if you want to work in miles, so this is equal to 11.179 kilometers per second. That's a big number. In 1 second, your satellite has to travel more than 11 kilometers in 1 second. And if you want, you can convert that to miles. And that's 6.9481. (6.948) miles per second. We typically remember this number about 7,000. So we say if you launch something from the surface of the Earth, the launch velocity has to be at least 7 miles per second for it to not come back to the surface of the Earth. The problem is when you're launching it from the surface of the Earth, the assumption of central motion and the assumption that no force other than this mg is acting on the object is not really valid. The density of the air at the surface of the Earth is not small. It changes from place to place based on the local altitude, based on the temperature in the air, and so many other things. But it's not zero, okay? It's more than 1 kilogram per meter cubed, okay? And the drag force is not really going to be a super small force. So I'll just show you what will change in your equations. I'm not going to derive any analytic solution for it because there is no analytic solution and I cannot decouple it. It's going to be highly nonlinear, but I'll show you. So you have to solve it numerically and I'll show it for you. But your equations would change, and the number that you need is way, way bigger than that 7 miles. And typically they do not really launch anything from the surface of the Earth, okay? What they do is typically they send it off to an altitude of R0 by a rocket, and then at that altitude they change the direction of the thrust and they give it the initial V0 at that R0 and then let go. Okay, so even from the surface of the Earth, if you see here, they never, because initially you need to give it this V0 speed like that, right? And if R0 is equal to RE, what happens? It is going to go tangential to the surface of the Earth, and guess what? If you have something like a big mountain here on your way, it's not going to be any nice. So they typically lift it up to a big altitude when they are sure that it's not going to hit something and the air density is really small. So their equations like this are much more credible. And then, so it's 2 parts of motion. First, they bring it from here to here. In this case, you're using the thrust force, which is not shown in my equation. Then you change the direction of the thrust, you rotate it from this direction. Let's say if this is your satellite with the rocket, correct? Carrying this guy. Then they rotate it like that, give it some initial thrust with speed of v naught at this r naught, which is definitely bigger than r of the Earth, and quite bigger, and then let go. Okay, so it's two parts, and all we have considered here is just the second part. This launching it from the surface of the Earth to that r naught is a separate topic. And in one of my future videos, I'll talk about the motion of the rocket, for which the mass is variable, and so the Newton equation has to be written in its original format, F equal rate of change of momentum. So I'll talk about this first part separately later. What we are only looking here is at a constant r naught and with initial speed of v naught tangential, what happens. But as I said, here, when it is doing its motion in the second part, we are neglecting the effect of the air, assuming that what? Your air density is low. In general, that is not the case. In general, what you have, again, depending on this R naught, you might get some drag. Even though not huge, you still might get something. So if you want to include the air drag, then you have to look at the speed of this object. So this object has two components. One of them, so this is the overall speed of this guy. It has two components, so this is the speed of the velocity, sorry. This is the velocity of the satellite, and it has two components. This component, as I said, is r dot, and this component here is going to be r theta dot. And then here you can consider this angle alpha, which is different from theta. Okay, it depends on the relative magnitudes of the components of the velocity. And then opposite to the direction of this v, you have the drag force. So you have this force here. And so not only now you have your weight component, you also have your FD component. And so what happens to your equation? So now some forces along the R is not only going to be that negative mgre squared over r squared. If this is alpha, then negative FD cosine alpha is also going to be added, and this is equal to now mass times r double dot minus r theta dot squared. And in the theta direction also, you will have, as you can see, negative f naught times sine of alpha. This is equal to m times r theta double dot plus 2r dot theta dot. So your equations are going to be more complicated. And how complicated are they? Well, let me show you what happens to your equations. Well, alpha is tangent inverse of r theta dot at any point over r dot at any point. So angle alpha has to be calculated all the time and plugged in into these equations. So this guy here has to go here and here, And so you will get sine and cosine of tangent inverse of r theta dot and r dot, which is a highly nonlinear term, plus Ft itself, the drag force, is what? It is 1/2 rho A CD times x dot plus y dot, or magnitude velocity dot, which in this case is going to be r dot squared plus r theta dot squared. So this term would also appear in your equations. So it comes here and it comes here. So you see your equations are going to be highly nonlinear, right? And worse than that is this part here. These terms, rho, A, and CD, that in many simple applications like a trajectory on the surface of the Earth, you might consider them to be like some simple constant numbers. They are not. CD, this coefficient, the drag coefficient, does depend on the speed. So the CD itself is not a constant number. It depends on the Reynolds number, and it does depend on, of course, the speed. So this guy is a function of v, where v is the square root of this, correct? So it's not really constant, and the fact is I don't think we have data for all different v's that a satellite might, or we might have to some extent, but it's not really easy to get the drag coefficient for like a satellite on all ranges of velocities it can have. The harder than that is the density of the air. The density of the air, rho, is a function of what? It is a function of r, the distance from the Earth, and a bunch of other factors. It's not just the distance from the Earth, but that's the major factor. So for different layers of atmosphere, the density does change. And as I said, if we neglect this or say this is very small because r is big, then yes, we can neglect the drag force and these drag terms would gonna go away. But in general, if you're launching it from the surface of the Earth or close, this rho is not zero, and as it goes through one layer of atmosphere to another, the density does change. And even this A is not constant. This A also does change, okay? Because if it's a sphere, then the cross section in front of the air that is coming, correct? So let's say it is moving like that. And here we consider this angle alpha. If we assume the air is stationary, which is not really. We assume the air is stationary, then the angle between the motion and the air could be considered like alpha. So this alpha, we can consider it as angle of attack. While again, the air in general is in motion, so the relative angle between the motion of the satellite and the incoming fluid is not going to be alpha. It's going to be alpha minus or plus the angle of the air with respect to a reference, like a inertial reference. And then unless the cross section of the satellite is a sphere, which if you look at it at any angle, the cross section is always pi r squared. When the satellite is of specific shape, then when you cut it at different angles or look at it at different angles, then you'll see that this A is going to be really a function of alpha. Depending on at which angle of attack you're looking, which part is in front of the air coming, then the cross section also does change. So yes, this drag force is very, very complicated if you want to look at it in very good detail. It's not as simple. Okay, so here we made life easy by neglecting this drag. Otherwise, my equations would be extremely complicated. No analytic solution, and even numerical accurate is very hard because we don't know a lot of things about these rho, A. A we might, yes, A is not that bad if you have the CAD model of Our satellite, we can look at it at any angle and get A. CD, maybe we have some good results from wind tunnels at high speed. The hardest part, as I said, is rho, okay, for which we have to use a lookup table for different layers of atmosphere and for different conditions. So even solving this perfectly realistic with numerical solvers is a daunting task. Okay, and here for the last part, I have shown you I will show you, I haven't shown you, I will show you the simulation in Simulink of a satellite. So here I provide the constants of R naught and V naught, as well as, of course, G and RE. And these two sets of solvers here, you see here I have one line that is taking R double dot, converting it to R dot and R. The other one taking theta double dot, converting it to theta and theta dot and theta. And then sending theta and R out, as well as X and Y, which are R cosine and R sine of theta. So if you look at the governing equations are very simple. And this is that mg term, which is modified. For theta double dots, there is no term, it's simply 0. And not theta double dot, it's not 0, it's just equal to the rest of the terms. So if I want to solve this using Simulink, what I need is I look at these equations 1 and 2 and I solve them for R double dot and what? Theta double dot. So if I want to use Simulink, this is what I do. I say R double dot is equal to what? It's equal to negative GRE squared over R squared. Correct? And then take this term also to the other side. And from the bottom one, I find theta double dot, which is going to be 2R dot theta dot with negative sign divided by R. Okay, so these are the highest order of derivatives for R and theta, and I get them from R theta, R dot theta dot, and the constant term. It's not really constant because it depends on R. I form these guys and then I double integrate them, and this is exactly what you can see here in Simulink. This is R dot at time 0, which is 0. Remember, I said no radial velocity at lunchtime. This is R of 0, which is R naught. This is theta of 0, which we consider 0, and this is theta dot at 0, which is equal to V naught over R naught. Okay, because remember V naught is equal to R times theta, so theta dot is equal to V naught over R naught. And this is that 2R dot theta dot divided by R. So that's all it is. I provide the final simulation time, and then I run this whole thing from my MATLAB script. So here I'm doing a simulation with some speed of 90 to 40. Okay, which is between the escape velocity of 11 kilometers and that guy divided by square root 2. Remember, this is the escape velocity. The circular velocity, circular orbit velocity is this much, 7.9 kilometer. 11.2 is escape, 7.9 is circular. So here this number is between those two, 9.2 kilometer per second. So I expect an elliptic circle. This is the radius of the Earth on average. This is the launch velocity, which, as you can see here, it is 230,000 meters above the surface of the Earth, or 230 kilometers. So at an altitude of 200, the difference between these two, 230 kilometers above the Earth, I will launch the satellite with 9.24 kilometers per second. This is my simulation times in second. This is my eccentricity. And then here I'll tell you based on what's calculated for eccentricity, I will have what kind of path. I run my Simulink file, and then here I plot the Earth for the reference. I plot the orbit of the satellite, and then I will animate the motion of the satellite as well. So here we go. And I also show you Rmin and Rmax of the satellite on the orbit. So here, the blue circle is the Earth, the red is the path, and the black one is the satellite. Clearly you see it is an ellipse. The minimum distance is 6.6 million meters, or 66,000 kilometers. 6.6, right? Or 6,600. 6,600 kilometers is the minimal distance, which is the R0, the launch radius. And the max is happening when your satellite is here at angle of pi, and that is, as you can see, 15,000, 16,000 kilometers. So 6.6, right? 6.6 thousand from the center of the Earth, not from the surface of the Earth. 6.6 thousand from the center of the Earth, or as I said, 230 kilometers offset from the surface. And then this one minus that, which is about 10,000 kilometers. So it goes from 230 to 9 to 10,000 kilometers off the surface of the Earth. Okay, clearly you see the motion was elliptic. Let me simulate it one more time. You can see the animation. And I chose my final time so it goes more than one round. And then stops. And if you look at the value of your E, it is 0.42, which is, as I said, between 0 to 1, and that means the motion is elliptical. Now, if you get it closer and closer to that 7.9, then you expect, of course, that is for from the surface of the Earth. Here we are not launching it from the surface. We are launching it above the surface. So this number is going to change, right? You remember the formula that we had for the circular orbit, let's say. Let's see if I can find it for you. It does depend on R0. So when R0 is getting bigger than RE, right, then you will definitely get a smaller number required. Okay, so here I don't need as big as 7.9 to make it circular, right? If I make it 7.9, still it should be elliptic. Let's take a look at that. Yes, clearly see. Definitely you have Rmax and Rmin to be different. So you need to make it a little bit smaller to make it circular, right? Because you are not launching from the surface of the Earth. And we can calculate that based on this R0. It's not really hard to calculate. And then if we make it bigger, like very big, last time it was 90 something, let's make it like 11,000. See what happens. If we can go to parabola, there we go. Yes, we do. Clearly, you see, I'm going on a parabola right now, and I'm not going to go back to the Earth. If you look at the number, it's 1.01, right a little bit above 1. So it's really hyperbola, but very close to parabola. Why? Because my number is almost 1, so it was a very good choice. Now, if I make it a little bit bigger, now it is going to have a bigger slope, and it's going to go hyperbola, which you clearly can see. Right? So depending on where I want to go in the solar system, then I can choose a parabola, hyperbola, or so on. Okay, but you clearly see you're not going to come back, and here you see it's 2.02. Okay, so I hope you learned how to determine the motion of the satellites from their initial conditions, analytic solution, what happens if you bring in error. I showed you some simulation in MATLAB, and I'll see you in the next lecture. Thank you.